Hello everyone, today I'm going to deliver a lecture on approximate vertical load analysis. The course will be overcome the approximation based on the hinge location and assumptions and example of the approximate vertical load analysis. These are the main basic and main purpose of this lecture. Along with additionally, I will try to deliver a lecture with moment shear values we using coefficient, and then example of approximate vertical load analysis using ACI coefficient method, which is moment shear using, and then compare the bending moment diagram between approximate vertical load analysis and the ACI coefficient analysis. We have been found the ACI coefficient analysis gives the better results. And okay, let's start the approximation based on the location of hinge and assumption. Okay, so I'm going to the slide. This slide or this handnote is made in Professor Dr. Iftekhar Anam sir, Professor University of Asia Pacific, Dhaka, Bangladesh. Okay, so here is the approximate vertical analysis and approximation based on the location of the hinge. If the beam AB is given here, is subjected to the uniform distribution vertical load. W is a unit per length is fever given is 1 and both a joint A and B. This is A and B shown figure B because of the although the joints A and B are the partly restrained from the rotation, the restraint are not completed. Head and B are completely fixed. If the figure is given the fixed, and the point of inflection would be location in distance 0.21 L from the each end. So this, if the fixed end is it will occur, then the inflection will be 2-1. But in practically it is not impossible. If on the other hand in A and B is figure D, we have been seen D, and the point of zero moment at the end of beam for the actual case of partially fixity, the point of inflection can be assumed somewhere 0.21 L and 0 from the end of the beam. For approximation analysis, they often assume to locate at the 1/10 of the span of the length of the each joint. So we can see in the figure D, so the inflection point will be 0.1 from the left and right point of the each of the side. So depending on the supportive condition, hinge end fixed or other continuous, the beam will be generally can be statically indeterminate up to the degree of 3, and therefore make it statically determinate. The following three assumptions often of the vertically loaded analysis of beam. So one is axial force is 0, axial force of beam. So we can see the beam, there is no axial force, and the point of inflection occurred at the distance of 0.1 length measure along the space of the right and left support. So these are the our approximate location of the hinge. Okay, so bending moment of the shear force of the approximity analysis, we can see the moment will be 0.01 square divided by 8, which is 0.088 square for mid span. For the negative span, we will found the WL square be 8 minus 0.018 square, which is 0.045 L square at joint A and B, or we can say negative. For the shear force, the positive and negative at joint and B, WL by 2 and B will be minus WL by 2. Okay, let's see. Before I'm going to the example, so if UDL is occurred is here, and we can see this is divided 0.1 and 0.1 and this is the 0.8, then the diagram will be like this. If the taking the positive moment, I'm just scrolling here 0.8. If we take this only this part 0.8, so if we take the moment WL square by 8 is L is 0.8, so we can see here L is 0.8, and in this way we've been found the positive moment is here 0.08 square. But we can using another formula for from this figure, we can see here is a W, and if that length is 0.8, then we can that divided W into L divided by 2 and W into L divided by 2. So moment will be W into L divided by 2 into 0.8 into L, which is 0.08 L square. So it will be same as it is, but I will recommend for this. So for negative moment, so we can see this is the negative moment which occurred in the left side and right side. So I am seeing left side. So W into 0.8 divided by 2, it is occurred. We have been seeing it, if we cutting this here, then we can see this load is here in upward. For balance purpose, it will be downward. So now we are taking the cantilever method. We have been shown W into 0.8 into divided by 2. This is the force, and distance is here 0.8. So force into perpendicular distance for this. And now for this one, we can see WL square by 8, W into L. L is what? 0.1, 0.1 square divided by 8, and found 0.04 L square. So negative moment will be 0.045 WL square. Or we can using this formula for getting the negative moment, which is 0.08 L square divided by 2.1 into L plus this formula, and finding this below. So if you go to the another book, which is RC analysis using Hibbeler books. So if we can see here clearly shown the figure on the fixed support. Then it is the inflection point is 0.18, but it is not possible. For this is the girder. For the simple support, we have been seen here the point is 0 moment is here, and the approximate cases we can assume 0.1, the assume to be 0.1. These are our cases, as I have been shown why how we'll get this formula and how to derive this. So this is our we have been found from this formula. I have been shown why you have been using 0.1 and 0.2. Okay, so let's see another book, structural analysis by Reddy. So continuous beam, we can see here the distance 0.1 from figure is given, and 0.2 is given. Here 0.21 given is here in left and right side, and we can see 0.25 also given. But these are not getting exact or satisfactory result. On the other hand, we can see how the satisfactory result can be found obtained the selecting of the fraction of point 0.1. So we can see here another graph is here. When the inflection point is left and right side is from 0.1, then it is found a satisfactory result. That's why the 0 point will be used. Okay, now we can see the moment share values using ACI coefficient method. We have been seeing the lots of positive moment is here. The positive moment if end span is discontinuous is here, and interior is here. If you go to the the efficient coefficient method, if you go to the book of the Nilsson, then we can clearly understand how we'll get. This is the Nilsson books, RC designed by Nilsson book. We have been finding all this below. If you go to the this figure, we can see figure 1, which is a beam with more than 2 span. So more than 2 span. The positive moment is 1/16 is given here. 1/16 the interior span. If that the end span, if the discontinuity in this discontinuous, then it will be 1/14. On the other hand, for a negative moment, we have been found 16. We've been found 11. I will get 11. 11 is gained negative moment, and the other face of the interior support 11. So we've been found this is 11. This is 11. It will be 14. So let's see. I hope you can understand. We have been covering this approximate location of the hinge. Now we can see the example of approximate analysis of vertical load analysis. Okay, let's see. So these are the our diagram we have been seeing. The one keep load is UDL load is given here, and 10 feet, 10, 15 feet, 10 feet, 15 feet, and 10 feet, 10 feet, and 12 feet. So analyze the three-story frame structure located in shown below using approximate location of hinge. Draw the axial force, shear force, and bending moment diagram of the beams and columns. So for 15 feet beam, so we can see this is the 15 feet beam. The positive moment WL square by 8, the L will be 15, that's why it will be 8 kip per feet. So negative moment we can see 0.08 WL square, which is found 10.1 kip per feet. So how we'll get 0.04 and 0.08, I have been shown here from the derivation. So you have to memorize this method or equation. You must be memorized, otherwise you cannot solve this. For the shear purposes, WL by 2, so we have been found L is 15, that's why you have been found 7.5 kip. In the same way we can analyze the beam which is 10 feet. We have been shown here that this is the 10 feet beam. So we are using the same formula, which is M positive equal to 0.08 WL square by WL square. So how much will be L? L will be nothing but only 10 feet, because we have been only analyzed the 15 feet. Now we can solving the 10 feet of the beam. So in this way we have been found 10 kip per feet. In the same way we have been using the same formula, which is negative moment, which is M negative 0.045 WL square, which is 4.5. We have been seeing 4.5 kip feet, and the shear value will be WL divided by 2, which is L will be 10, that's why it will be 5, and the axial force is all member is 0. Okay. So we have been finding from here we can take 10.13. So we have been found 10.13 for the negative, 10.13, 10.14, 10.14, 10.13, 13, 10.13, 10.13. Sorry, and we can see here for changing the color, the positive moment we've been 18. This is the 18. This is the 18. This is the 18 because this is the 15 feet length. 18, 18, 18. And for 10 feet length, the positive moment will be 8 kip feet. This is the 8 kip, 8 kip, 8 kip, and the negative will be 4.5. This is the 4.5, 4.5, 4.5, 4.5, 4.5. So bending moment will be this this diagram 0.08 WL square and minus 0.04. If you want to if you want to rewrite 0.08, you can write 0.1 WL square by 12.5 instead of 0.08. So same as if you write the 1 divided by 12.5, then it will be 0.08. On the other, in the same way, if you write the 1 by 22.2, then it will be 4.55. It's euro wise. Okay, now we can see the shear force WL by 2. We have been found 7.5, 7.5, as we have been seeing. This is here 7.5 for 15 feet beam, and 5 kip for length 10 feet beam. So you can see here. So axial force we have been how we'll get the axial force. This is the 7. This is the 7, and this is the 7. This is the 12.5. How we'll get this is 7. That means this is also 7. 7 plus 5. So this will be acting here. 7 plus 5. It will be 12.5. So in this way 12.5 and 7.5 into 5, which is we have been seen these are the 7.5 and 5. It will be 12.5 and upper 12.5, it will be 25. In the same way we have been found here 7.5 plus 7.5, which is 12.5, and upper is 25. It will be also adding, and in this way we will find 37.5. Now we can see this is the important for bending moment of column. How we'll get the bending moment of column? So we have to keep in mind bending moment is column is forming bending moment of beam H1 divided by H1 divided by H2. So if you shown here, I'm just giving here. Okay, here this is the coefficient. You just you just showing how we'll get 10.5. It's top, the bending moment at top is from 10. This is the here 10.13. How will get 5.06? 5.06 will be coefficient, as we've been seen here. This is the coefficient and multiply with the bending moment. So coefficient, how much? How will coefficient EMB? How what is the EM? This is the I section IM EA. So EM divided by EM by IE. So these are also, we've been seeing EM, that means this length is 10 feet, and EM plus IM also this length. So we've been founding this length and this length, which is 0.5, and multiply it into 10. Okay, so I'm just erasing again, showing another color here. Here 10 into 10, sorry for interrupt. 10 divided by 10 into 10, which is 5, and it will be multiplied with the bending moment of column. We have been found 10.13 and found 5.06 here. So for this purpose, I will get 5.53, which is AE. That means AE is this portion, and AE divided by EM, this is this portion. Then AE is 12, and 12 divided by 10. These are the coefficient, and found 5.5. 5.5, it will be multiplied with the this bending moment of beam, and founding 5.53. Okay, so bottom, how will get the bottom? Bottom nothing but in the top we have been found 4.6, and it will be divided by 2, and that's why it will be 2.3. Okay, in this way you have been also, you can calculate here, and it is taken from bottom. It is unbalanced. As we have been seen here, unbalanced. How will get this 5.6? It is the same as 6.08. How will get this 5.3? So we have been founding here 10.13, and this is the unbalanced 4.5. So we've been if we go there 10.13 and 4.5. So if we deduct here, then we will found a 5.63. In this way we've been found 5.63. Okay, here here this is the 5.60. So I will get there, this is 5.63. It will be multiplied with the coefficient here, h1 minus h2, as we have been seen here, h1 minus h2. So h1 minus h2 is 15. So 5.63 into 2.21. So in this way we can solve this here from this portion also. Now you can see how we will calculate the shear force of column, but it is not needed. So 2 into M average divided by L H. What is the M average? M average is nothing but we can see here the M average is here 10.13, and here is a 5.06. So divided by 2, which is 7.596. So shear force of a column, which will be 2 into M average divided by H. So 2 into M average we have been from 7.595, and H is nothing but 10 feet. We have been shown in our figure here is a 10 feet. Okay, and in this way we have been from 1.5. In the same way you can calculating here. Okay, these are the main purpose of this lecture. So now we can see the moment and shear using ACI coefficient. This is the extra lecture. So you can, if we go to the here, we can see here the positive moment we have been shown here, discontinuous, as we have been already shown. If you go to the Hibbeler, if you go to the Nielsen book, figure number 12.1 and table number 10, 12.1 and page number 407, then we have been found here. So I'm just going here. This is the moment and shear below coefficient. These are taken from the Nielsen books. The positive moment we have been found this value, as we have been already shown the positive moment for more than 2 span is 1/16. This is the you can memorize is 1 by 16. For 1 by 14 will be applied when the in this span if the discontinuous in this integral with the support. Okay, and another we can memorize the 1 by 11. 1 by how will 1 by 11 by negative moment on the other face of the interior support. Okay, so in another we have been shown negative moment on the interior face of the exterior support is built in integral with the support is spandrel with girder, so it will be 1 by 24 WL square. Okay, these are the ACI moment coefficient. It is taken from here. Okay, so let's see how we can solve. So I'm just seeing here. So we can see the ACI coefficient pattern. So if we using the shear force diagram, okay, I'm just we just seeing the positive moment as we've been shown here from this coefficient or from this coefficient. So let's see how we'll get this value. So you can see here the positive moment. This first of all we'll complete here. So WL square divided by 14, L is given is 15, so W 15 square divided by 14, and we have been found 16.07. so positive moment another which is for length 10 feet, so I will get this. So WL square by 16 for interior, so WL 10 square divided by 16, and we've been found 6.25. For negative moment we have been found WL square by 16 and L is 50 square, and we've been found 14.04. So in this way we can found in here the shear force and axial force will be found in the same way as given here. For getting the shear force all in first exterior 1.1 WL divided by 2 and WL divided by 2 for all other section. The shear in int member first interior support or other member WL divided by 2. So if we calculate it here, then we will be found shear force, and axial force will nothing but it will be the sum of the interior as we've been shown here, the sum of the load of the shear. So I hope then this also in depth and example also in depth. So now we'll compare the bending moment approximate analysis method and ACI coefficient method, which is much greater. So we can see here the ACI coefficient method beam bending moment, and here the beam bending moment approximate method. So we have been shown the 18 for exterior bending moment. For ACI coefficient we have been found 16.07. Okay, so we have been found another interior moment which is 8, and we have been found 6.25. so we can see the bending moment of beam is much greater in approximate method. So you can see another in interior for negative moment which is 14.08. On the other hand we have been found he has 15.63, and we have been found 10.03 and 4.5, 14.50. So you can see the negative moment is greater for ACI coefficient. For on the other hand the positive moment is greater in approximate method. So we can see so this will be not a conclusion. Positive moment is more for ACI approximate method, and negative moment is more for ACI coefficient method. So you can see here we can see we are seeing again. So approximate method, you can see the positive moment is 18. On the other hand, the ACI coefficient method we have been found 16. For interior we have been found the 8 and we have been found 6. So you can see the positive moment is much greater for approximate method. ACI coefficient method we have been found the negative moment is 15, but we have been found 10. So you can say the ACI coefficient method is much more. So lecture is in depth. If you have any question, then let me know. I will try to cover your answer. Before going here, I'm just showing examples here again, because these are the focus on lecture is approximate vertical load analysis. So let's see again. This is the our example. So you can see we can use the positive moment diagram, which is WL using this formula and found 18, and negative formula is found 18, and in this way you can calculate, we can draw the diagram, bending moment diagram based on this formula. And SFT we will use WL by 2 and forming this formula, and shear force we will just adding this value, and subsequently add in the sum of the shear and shear. So these are the importance how we'll get the bending moment of column from bending moment of beam. So if we want to draw the bending moment of column, so we have to using these 4 steps. So first is top, we have been found 13.3, so 10.13, so 10.13 we have been found. There is no doubt. I will get the 6.08. These are the found for unbalanced moment. So unbalanced purposes, if we deduct 10 minus 13 into 4.5, then we have been found the unbalanced. Okay, so how will get the 5.06? So it will be taken from as we, so these are the coefficient we have used. This is the coefficient and this is also coefficient. I will get the coefficient. Coefficient is nothing but h1 divided by h1 minus h2, and it will be multiplied to the bending moment of beam. So let's see. At first we have been seen EMI and EM divided by EMI by MI. So what is the EMI? So we have been seen here. These are the I, M, E and I. So MI is here and EM is here and I is here. So we can see here, if we taking this this calculation is here, so I'm just copying here, then you can understand how. Okay, so bending moment of we can draw here. So we can see here EM, this is the EM, that means this column length, divided by EM by MI divided by this length. So at first this length is 10 feet and divided by 10 feet by 10 feet, and this, and multiplied with the bending moment of beam. So 10 feet by 10 feet, it will be 0.5, and it will be multiplied with the beam bending moment of beam, and in this way we've been found 5.05. Okay, so let's see. Let's see another one. Here I'm just copying this. I will get this value. Okay, for this getting for this moment, so we are just watching AE. This is the AE, this is the length, and AE divided by EMI. So AE is 12. So 12 divided by 12 plus 10, which is 5.5, 5.00, and it will be multiplied with the bending moment of beam, as we have been seeing 10.13. So 10.13 will be multiplied and found 5.53. So in this way we have been found 5.53. This is the 5.53. And last one we can see, it will be how we'll get this value. It will be AE divided by 10. If we calculate here, 10 divided by 12 plus 10, which will be, it will be 45.45 in, it will be multiplied by 10.13 and founding 4.63. I will get this also, and the same way. And after this getting this value, so the diagram will be like this. Why? Because it will be depends on this value. So as you can see, this value is getting left side, that's why the diagram will be this like this, and inclined from left to right to left. And another one we can see here, the incline is getting for left to right, that's why it will be getting from left to right. Another, the first one is we have been seeing the right to left, this incline, that's why the diagram will be the incline of right to left. And it will be vice versa because of the slope of we have been seen left to right, so that's why it will be given left to right. And the shear force diagram, how will get the 2m, m is mean average, how will get the average, we have been seen 10 into 5.06 and we have been found 7.595 and 2 into 7.595 divided by h will be how much? It's 10, and in this case we have been found 1.53, and in the same way we can calculating here. So after that we can see the ACI moment coefficient as we go to the Hibbeler books. Then we have been found the at first I want to draw the positive moment, which is 1 by 16 and 1 by 14 for exterior, and interior 1 by 16. And the negative moment will be for interior 1 by 11 and 1 by 11, and for exterior 1 by 12. So in this way we can calculating here, and we have been found the positive moment is much more. We have been seen approximate method, we have been found 18. For ACI coefficient method we have been found 16. So we can say that the approximate method is much more better than ACI method for getting the positive moment, not negative moment. So the negative moment we have been found 10.13 for approximate method, and ACI method we have been found 15.13. So we can see the ACI method is much more better for getting the negative moment. Okay, I hope that you can understand. If you have any question, then let me know. Thank you everyone.